Okay, so find the Haber Process Lab on Schoolbox, and then you can just jump straight to the unrestricted simulation. So this is the Haber Process. Just press Start, and you're going to turn this on. So you're going to get nitrogen and hydrogen of this temperature and pressure come in, and then it's the reacted material is going to come out here. Ammonia has a lot of polar bonds. It will condense at a lot cooler. It will condense first, and the other gases won't because they've only got London dispersion forces, and they'll get recycled and put into the machine again. So you're trying to obviously make a profit, so it costs money to put temperature and pressure in, and it costs money to recycle it as well. And so that's what you're trying to balance out. So it's fairly complicated. You want to use a catalyst. People don't. It's widely used, the iron one. The advanced is not so. I think that actually costs a lot of money. I think they're working on that. So the iron catalyst, it either holds it in a better 3D orientation, or it lowers the activation energy. If you have a careful look here, it looks like it's decreasing the activation energy. It looks like it's actually grabbing the nitrogen and ammonia and doing part of the reactor already and breaking it up into single molecules ready to complete the reaction to NH3, rather than orientating it as far as collision theory is concerned and speeding up the rate of reaction. So we go back to here. So we're trying to get a profit, and we have an exothermic reaction here. Pressure is 4.2, so increasing pressure should increase the yield. Increasing temperature is going to decrease the yield but speed up the reaction because it's at a higher temperature. So as far as I can tell, the correct answer, if you just type this in, this is 452, and this one here is 221. Press continue. And so I think the best answer you can get is close to 20, 19.79 or 80. And so what you're going to do is you can try and find a better answer, but I'd advise you watch this video first. So let's try and increase the pressure. So if I increase the pressure to 222, you'd think that would cause the production to go up. But the production costs also go up, so the profit will go down. Potentially, you're not quite sure. It's a bit of a balancing act. So 19.7, 33 and 4.41. So that does go up slightly. That one there. And the production does go up slightly as well, but the profit goes down. Okay? And so we were better at 221. So let's keep it at 221. And you see it's, let's go to 220. All right, so I'll type in 220 rather than slide it. And there it drops down quite a bit again. The production costs actually go up, which is the weird thing. And of course the amount of ammonia goes down, but we thought we might have, because we've made the pressure less, it would have been cheaper. So that's the one that doesn't make a lot of sense. So what it seems is going on is the production costs actually go up, because even though it's less pressure, the recycling, so you've got to repressurize and recycle and reabsorb this component here. And so you're increasing the amount here that needs to get recycled. So ironically, even though it's cheaper to decrease the pressure, it actually costs more over here, and the production costs actually go up. Okay, and so not only are you getting less ammonia, it's also costing more to recycle, so the profit is going up. Okay, so I'll take it back up to ideal, or what I thought was the best I could get, and let's do the temperature. So if we increase the temperature, we should increase the rate of reaction, even though we decrease the yield, and so potentially we could do better there. So let's increase that to 453. Even though that will cost more, it may be significant, and the profit goes down. All right. So just comparing. So the production costs went up a tiny bit, and the amount of ammonia we got went up a tiny bit, but the profit went down a tiny bit. Okay, so that's not the ideal. So 452 is still better than that. So let's try decreasing the temperature. Now, if I decrease the temperature, this should go down to 4.7, less than 4.7 because I'm using less energy. But it's slowing the reaction. It's exothermic, so this goes down. It's favoring that. So the yield is better. We don't really care about yield because it gets recycled, but then we do care about yield because, as we've found out, it costs money, and that's the sort of the missing key here in your theory as far as what you've been taught about pressure and temperature. And so the profit, it'll be interesting to see what the profit is. Let's reduce that to 451. I think this is glitched out because that hasn't reset. I'm going to reset this. So the computer also glitches out as well. This should be 221. Profit should get back to about 20. Yeah, 19.8, 19.79. Okay, so that it glitches out too. So you have to be, even if you think you've got an answer, you'd have to reset it and try it again because you can't trust this computer program. So 451 is what we were going to do. So we're going to reduce that. So the production costs go down a tiny bit. And what you're going to see is, so we're reducing that, it's slowing the reaction down. So the production has gone down a bit, and yet the profit went down. So that doesn't make a heap of sense either, unless you realize that there's energy going into taking those gases and compressing them and putting them back in here at the correct temperature and pressure. And so this part is, this cost is going up as well. All right. And so you need to sort of understand that because otherwise, I don't know, this is not that easy to understand. Okay, see if you can do better than the 452. There might be some other combination I've never thought of, but it seems like 452 and 221 are the best results you can get. And you're not allowed you're not allowed to use an advanced because they don't really, that's not used. They've got a lot of other advantages, disadvantages, so they're not widely used. And it's not working either. So reset it, 451222. Sorry, it's 452 221. And there we go. It's a bit fiddly.